Hello and welcome back to Math 055. This is a section over 7.7 and we're going to be talking about right triangle applications. Now, there's going to be some real talk right about now. All right. This is one section that I do not mess around with. Okay. Because, as you guys probably don't know me that well, you just know me as the video guy and the math guy and the guy who bugs you with emails and, stuff like that. I tend to get a little lonely sometimes. And sometimes making friends for a math teacher is really hard. A lot of times, growing up, I would go to parties and, in high school and college, and I'd show up and I'd bring my math stuff, and everyone would sit there and be like, Joe, like, why are you bringing your math stuff to like hang out? Like, we're playing, I grew up in the 90s, so 64 was pretty big. Nintendo 64 was pretty big, and I would prefer to do math problems when everyone else was playing video games. And it kind of progressed through college, and I felt like in college I would meet people, that were like-minded, that wanted to do math all the time. And I tell you what, like, even like the nerdiest of nerds would be like, dude, I really don't want to do that much math. And so, it's a personal thing. And, it's a problem that I have with a lot of, building relationships and friendships like that. But, it comes to a point where you got to figure out who your friends are and who they aren't. And I found a lot of friendship in a person named Pythagorean, because he was always there. He was there every Friday night that I would, come home, and I'd say, hey, call people and say, hey, what do you guys want to do some math? And they'd be like, no. And I'd be like, and I'd sit there and I'd look across the room and I'd see Pythagoras just sitting there, and I'd be like, do you want to do math? And he would always want to do math. So, this is my favorite section because this is about my friend Pythagoras. And there are often times when I'm trying to find the length of a length of a right triangle given the other two lengths. And because of Pythagoras, because of my friend, we can do that. Okay. And so, from Pythagoras, what we know is that given a right triangle, if I take, the sides, okay, call these two sides legs, okay, and if I square those two sides and I add them together, that is equal to the hypotenuse, which is the longest side, which is always across from my right angle, squared. Okay, so a squared plus b squared equals c squared. You've probably seen this before. And the cool thing about it is, and the reason why we're introducing it in this section, is because we use square roots to solve for those other sides of a triangle. Okay, and it's pretty cool. And Pythagoras, in the lengthy amount of time that he and I have spent together, his favorite triangle is a 3, 4, 5 triangle. And this is something that pops up all the time. So if your length here is 3 and this length is 4, let's figure out what this last side is. Okay, so here's what I know. I label my triangle as A, B, and C. Okay, and if I use my Pythagorean theorem, I can say that 3 squared plus 4 squared is equal to C squared. Okay, so 3 squared gives you 9, plus 4 squared, which is 16, and that's equal to C squared. Okay, and so then 9 plus 16, that gives you 25. All right, and what I want to do here is solve for C. So to undo something squared, to get rid of that, I do the opposite of squaring something, which is taking the square root. Okay, and so what we end up getting is that 5 is equal to C, okay? And that's that third length. Now, what we call this is a Pythagorean triple, okay? Now, the crazy thing is that this is Pythagoras' favorite triangle. He loved triangles that were nice and even, right triangles that had whole numbered sides, okay? He thought this was the coolest thing. Now, Pythagoras back in those days was a political leader. Believe it or not, people that were educated were the political leaders because they were the smartest. Interesting how things have changed. Now, I digress from that conversation, but he was the one that made the rules. So Pythagoras was a political leader. It was kind of interesting because he only believed in whole numbers. He didn't actually believe in numbers between whole numbers. He didn't believe in fractions. So let's think about something else. Okay, let's say that you had a triangle that was a 1 by 1 triangle. Length of 1, length of 1. We're trying to figure out that length here. Okay, so if I use Pythagorean Theorem, A, B, and C, I get that 1 squared plus 1 squared is equal to C squared. Okay, 1 squared plus 1 squared is 1, okay, and then C squared. So then 1 plus 1 gives you 2. All right, so you get that 2 is equal to C squared. All right, and you take the square root of both sides, and you get that C is equal to the square root of 2, which we can't evaluate. Now that number is approximately like 1.41. Okay, it's a decimal. Pythagoras actually didn't believe that this number existed. And because he had political power, anyone that challenged him, well, he would just kill him, basically. And therefore, that's why, we have these Pythagorean triples. These triangles are still very important, but it took a long time for that society to actually realize that there were numbers in between numbers. So kind of an interesting little tidbit of history. And yeah, Pythagoras is my friend. So, but what I want to do is use this concept to help us solve for other right triangles, okay? And so over here, let's take a look at this example. And before I do that, I want you to read this part up here. We're going to talk about this later on. When I take this, like if I had this problem, and let's just think about this. We'll come back to it later. X squared is equal to, say, 4, okay? If I were to solve this problem, you have to think about what x is, okay? X, if I were to take this number, some number, and square it to get 4, well, we kind of already know that my answer is going to be 2, okay? But the other caveat to that is that I could also have the value x equals -2. Okay, if I take 2 and I square it, that's going to give me 4. Okay, that works. If I take -2 and square it, negative times a negative is going to give me a positive, and that's also going to work. Okay, so when you solve these equations here, it's customary, and we'll do that in the next couple sections to talk about the fact that you would get both the plus and minus value of those when you solve them. But because we're talking about distances, the negative value of that is not needed. Okay, so we're just gonna, if we're talking about Pythagorean theorem, we're just gonna keep it positive. Okay, because he's my friend, and we don't say mean things. We're gonna stay positive with him. Okay. All right. So in this example, a rectangular plot measures 16 meters by 34 meters. That means I'm gonna draw a picture. Scattered pictures in the corner of my mind, memories of the way they were. Okay, so it's 16 by 34 meters, and it's a rectangle, so I'm going to put right angles in here. Okay, and it says, to the nearest meter, okay, find, to the nearest meter, the distance from one corner of the plot to the corner, one corner of the plot to the corner diagonally opposite. That was worded a little bit weird. So what we want to do is we want to find this distance here, okay, which we'll call C. Okay. Now what I know is that I have a right triangle, and that I have my legs, Lieutenant Dan's magic legs, over here, which we'll call A and B. All right. So let's go ahead and plug that into the Pythagorean theorem. So I get this. I get 16 squared plus 34 squared is equal to C squared. Okay. Now 16 times 16. Let's figure out what that is. 16 times 16 is 256. plus 34 squared, so 34 times 34, which gives me 1,156 is equal to c squared. Okay, now, what I want to do is this. I'm going to add 256 to 1,156. Okay, and that's going to give me 1,412 is equal to c squared. Now what I'm going to do to solve for c is I'm going to take the square root of both sides. Okay, so if I wanted to take the square root of 1,412, then that's something that I would need to put in my calculator. And so when I put that in the calculator to the nearest meter, it gives me that c is approximately 37.57 meters, but it wants us to round to the nearest meter. So what I'm going to do, here's my nearest meter, the 7 here. I'm going to look at my 5. Since 5 would make me round up, that tells me that c would be approximately 38 meters. Okay, so there's actually a lot of really cool applications to these types of problems, and let's take a look at the next one. All right, so what's cool about right triangles is that there are some special ones where, and they're all the same. And this is something that'll pop up in future math classes, like trigonometry and stuff like that. So, but what I know is that I have one triangle that's a special 30, 60, 90 triangle. And what I know is that the triangle, okay, has 3 sides, obviously, but the shortest of that side we would call x. The hypotenuse of that triangle would be double that length. It'd be 2 times x. And then the third side, the one that's the longer of the 2 legs, is that length x times the square root of 3. Okay? And that's going to be true for any triangle that has the angles 30, 60, 90. Okay. Otherwise, if it doesn't have those angles, it's not going to have that ratio of sides. Now in part B, we have a 45, 45, 90 triangle, which is similar. Okay. Similar concept. Both of these angles are 45 and 90. Okay. And the legs of those 2 triangles are both the same length x. Then the hypotenuse is that length x times the square root of 2. Now, I'm not going to get into why we have that. Let's just trust that that's what we have. But let's go ahead and answer these 3 questions, okay? And so it says, if in a 30, 60, 90 triangle, the length of the side opposite 30 degrees angle is 4 inches, find the lengths of the other 2 sides. So what I would do is this. I would draw my generic 30, 60, 90 triangle. Okay, I would call this x, 2x, and then x times the square root of 3, okay? And what I know is that the side that's opposite of my 30-degree angle here is 4, and that's what it tells me. So I'm going to call this 4 inches, okay? So now, if I wanted to find my hypotenuse, okay, I would just take 2 times 4, which would give me 8, okay? And then, so that's one side, and then the other side would be this length 4 times the square root of 3. And guess what, guys? We just leave it like that. And you're done. That's it, okay? So if you understand how this works, okay, how these sides are related to each other, you can solve for any of the other sides, okay? All right, let's take a look at this guy. It says the path of a baseball field is a square with a side length of 90. So I'm going to draw a square baseball diamond, okay? And I know that this is 90. Okay, so the side length is 90. Now in this square, all these side lengths are 90 feet. Okay, 90 feet, 90 feet. Now each of these angles are right angles. Okay, so it says, what is the distance from home plate, which is here, to second base? Okay. And round our answer to the nearest tenth of a foot. So here's what I know, okay? What I have is that this is a 45, 45, 90 triangle. And I know that because my legs are the same length, okay? And I have a right angle that connects them. Here's what I know. This is x, and this is x times the square root of 2. Now you could still use Pythagorean theorem, or you could use the ratios that we have up in these examples, okay? And here's what I know. X is equal to 90, okay? So my hypotenuse, which we'll call C, is equal to that length x times the square root of 2. So if I just plug in 90 for x, I find that my hypotenuse is 90 times the square root of 2. Now if I wanted to figure out what that length was, I'd just plug it in the calculator. And that's going to give me a distance of 127.27 feet. Now if we want to round it to the nearest tenth of a foot, that would be this decimal place here. Okay, so look at this 2. Since 7 is larger than 5, I'm going to make that go up. So my value for my hypotenuse, the distance, would be 127.3 feet. Okay, and that's that length. All right, so yeah, you could use Pythagorean theorem, but if the problems are easy enough, we can just do it that way. All right, now the last problem says in a 30, 60, 90 triangle, well, I'm just going to draw a picture of a generic 30, 60, 90 triangle. So 30 degrees, 60 degrees, 90. Okay, it says if the length of the hypotenuse is 14 centimeters, find the length that is opposite the 60-degree angle. Okay, so we're trying to find this length here. Okay, now here's what I know. Based on the ratios, this is length x, this is 2x, and the length that's opposite 60 degrees is x times the square root of 3. Okay, so what I want to do, if I figure out what x is, I can figure out what this side length is. Okay, and we'll call this side length here b. All right, so here's what I got. All right, I'm going to set up an equation that 14 is equal to 2x. I'm going to divide both sides by 2 and by 2, so I get that x is equal to 7. So this length over here is 7. But if I wanted to find the length of b, which is x times the square root of 3, then I simply just take 7, substitute it in here, and find that my length of b is equal to 7 times the square root of 3. Okay, now since they didn't tell us to round it to anything, I'm just going to leave it like that, and that's my answer. So, okay, that's all I got for this section. I hope you guys enjoyed this. I hope that you don't think I'm too weird because of my relationship with my friend Pythagoras, but I find that to be a sacred relationship. So hopefully you can find some solace in your relationship with Pythagoras as well. Get started on the homework and come by office hours if you got any questions. See ya. Bye.